Thank you, Martin. So, uh, what is before I start my talk, I'll say I've been associated with MIT some time, ERL specifically, and I did a sabbatical in 2014 here, and since then kept a close contact with a number of colleagues here. And my core area expertise is rock physics, and but I'm not going to talk much about that today. And I'll give a talk more on a wider project that we are doing related to CO2 sequestration. Now, what is interesting? It's not just CO2, but what is interesting, we talk about continuous monitoring. That is something, and fiber optics as a new type of receiver that is seismic receiver that is a new technology for measuring a seismic response, if you like. New type of sensor that opens new opportunities. It's most of this work, maybe not all, but is funded through so-called CO2 CRC, which is a non-government entity that collects also. It's a maybe joint industry kind of group that collects money from companies, governments, and to inject CO2 and do some research. Now, CCS, which is called carbon capture and storage, or probably the more common term here is geological carbon storage. It's basically injecting CO2 in the subsurface, and as a geophysicist, our task is to monitor that CO2 that is injected into the reservoirs. And the most useful technology is 4D, that is doing seismic time and again. And in one stage of this project, we did exactly that. So there was a CO2 injected into, basically this is infrastructure on the surface, it's a pretty small picture, but basically injected 15,000 tons of CO2 into a reservoir at 1.5 kilometer depth, and monitored with the, yeah.
Two kind of technical questions. Where's the carbon coming from? And is that, how long is that injected over that 15,000?
I'll tell you. The carbon comes from another field nearby, 4 kilometers away, which is producing 80% CO2, 20% methane by weight. So that's I mean, it's in Otway Basin. It is in Southeast Australia, in 150 kilometers west of Melbourne, and the Otway Basin has lots of old gas fields, small gas fields, and these gas fields are always have some methane and some CO2. Some have food grade CO2, which is used for producing fizzy drinks, and these are expensive. But the field that we use is, or CO2 CRC uses, is 80% CO2, 20% methane. Now, the Naylor field where we do the injection is actually had the opposite. It had 80% methane, 20% CO2. But we are not injecting into that, and it was donated to the CO2 community after the methane was depleted. But this injection is actually in the aquifer, which is good for seismic, because you can see, put gas into the water and it's gonna have a bright signature, called bright spot. So good for monitoring, but it wasn't obviously geared for monitoring, but it's good for us. So, and it was injected over 4 months. So it was a specifically designed array of geophones that was put 4 meters below the ground in the aerial pattern like this. So which helps in 2 ways compared to surface geophones. It reduces the noise and it reduces the annoyance to other land users, because you have cables on the ground and the cows will trip over and stuff like this. So this is actually farmland. So they were buried into the ground. And our group in the Curtin University is entirely responsible for all the aspects of geophysics for this kind of project. And it produced beautiful time-lapse images like this of the CO2 time-lapse. So this is a normal seismic section, and this is a time-lapse response growing within number of how much CO2 is injected. It was done every month. So the injection was 15,000 tons over 3 months. Did I say 4 months? 3 months. And after 5,000 tons, there was a monitor survey. After 10,000 tons, 15,000 tons, and then after 1 year and 2 years. And they're all plotted here. And you can look at how the aerial image varies as well. So the 4D works. But if you're gonna do a real size injection, which is not 15,000 tons, but like 15 million tons, or at least millions of tons, then it's not going to be practical to do 4D seismic or monitor survey every month. It's not going to work. It's too expensive. And if you do it once a year or once in 2 years, you may miss important events because you never know where your CO2 will go. So the alternative is continuous monitoring. So CCS, the monitoring needs to be inexpensive, minimal land footprint, have minimal land footprint, frequent or on demand, and basically the solution is continuous monitoring with permanent sources and receivers. Now, as a receivers, we use borehole dust, borehole fiber-optic sensors that I'll explain in a minute. And as a sources, we use surface orbital vibrators. That basically, you could say a vibro size cemented into the ground without any wheels. It's actually much dumber than a vibro size, because vibro size has all these signature controls, all these things. This is just a washing machine, basically cemented into the ground. So the system, I mean, I have to mention 15,000 tons is not lots of CO2. The aerial footprint is relatively small. It's hundreds of meters, not kilometers, not tens of kilometers, hundreds of meters. And the way it was done is that there were 9 permanent sources and 5 wells instrumented with fiber optic sensors. So 5 wells are receivers, 9 sources are strategically placed around the area, and all these lines are basically expected reflection points. You use reflection seismic. And what are these fiber optic sensors? I don't know if people in the audience know much about it, but distributed acoustic sensing is a technology that allows one to use optical fiber cables as seismic receivers. So basically, you have a fiber optic cable cemented behind the casing in a well, and you have this called interrogation unit that sends laser pulses through that system. And basically, it's schematically shown here. You have laser going, and through scattering of that laser pulse at different points in the cable, you can sense any strain or strain rate, changes of strain between these 2 points. So it actually sends 2 pulses, not 1, and these pulses, interference between these pulses changes if you have strain because you have they interfere differently depending on where it is happening. So the cable is obviously a complicated thing, but the important sensing element is these fibers inside the cable. Measure strain or strain rate, depending how you set that up. Strain rate being the time derivative of strain. So here's a little more on this, and actually different type of scattering give you a different value. So if you use Rayleigh scattering, that gives us strain or strain rate. If you use Brillouin scattering, it gives us some, you can use as measure static strain. This is the dynamic strain. And if you Raman scattering, which I don't remember what it is gives you temperature, distributed temperature sensing. I should say that basically it's called distributed these sensors because every point in the sensor in a cable is your sensor. Now, when I say every point, there is an effective length of that sensor, and that is set up in the interrogator unit. You can change it. There's nothing in a cable in the usual cables, I should say, in the usual cable. We can go talking about details because there are special engineered cables that are enhancing this kind of thing. But you can use a standard telecommunications cable, and it will have sufficient impurities to cause scattering, sufficient impurities along the cable, and you set it up in the system. Sometimes it's hardwired to the interrogator unit. Basically, the gauge length that we use normally is 10 meters, which is quite a lot, but it gives you a good signal to noise ratio. You get good signal strength. Now you can go but it's set up that actually the sensor is every meter, so there's kind of overlapping 10 meters, 10 meters, 10 meters, running average, if you like. So gives you a very continuous, smooth picture. But the effective length is 10 meters, and that's in all our systems that I show today. We use 10 meters, but I think over the years we will get to 1 meter and stuff like this because the technology is constantly improving. It's a very, very moving kind of technology. This kind of schematic, like you have, this is the dust measures strain rate, which is the difference between two geophones, you can say. And this is how technology evolves. This is impressive picture because this is our first attempt to use fiber optic sensing for seismic. This is a VSP seismogram, so this is depth. Well, I don't even know what it is, but this is time, this is depth. Horizontal axis is depth, and this is direct wave. So this signal to noise here and signal to noise here is completely different. And that's just technology. That's purely technological development. The same vendor, by the way. It's the same cable. Same cable.
Just different.
Well, I can't. I don't remember if it's the same cable or not. But I think even with the same cable, you would see similar gain. I'm not guaranteeing you it's the same cable. I'm not guaranteeing you that it's deployed the same way because the biggest thing is an interrogator unit, and next there's cables that have enhanced scattering. So the modern engineered cables have fixed points, fixed scatterers or reflectors, you can say. So it's no longer scattering. If you scatter Rayleigh scattering, you have to do enormous amount of optical processing because the scatterers that naturally occurred in the cable are not guaranteed to be exactly the same along the entire cable because they have impurities that nobody created on purpose. But in engineered cables, there are fixed points and much easier to handle, and it gives you much better signal to noise ratio. But for example, the engineered cable we use now has 5 meters hardwired these scatterers or reflectors, and you can't go to smaller, and they are more expensive. But if you put them in the well, that is itself an expensive operation. So you better as well use the best cable that exists.
Does that limit the gauge length that you can?
Of course, it does. But I mean, I guess they can make ones that are much finer. So they're working, all these vendors, Optosense, Selixa, the leading vendors, Halliburton, Terra 15, all sorts of companies that do this kind of stuff. They all working on centimeter scale gauge length now. So particularly for things like microseismics, where the vents are very high frequency. So these are the sources. Let's switch briefly to the sources. Rotational sources going one way, then another way. This is how they look actually. And we use mostly these dual motors, which gives you a broader bandwidth because you work with a low frequency and high frequency. We go over 100 hertz in this reflection seismic. I mean, I apologize. I wanted mostly to talk about continuous monitoring with the actually in the passive mode, but I have to mention sources because that was the mainstay of this project. So reflection seismic. So this is how it was done. 5 wells from 2 platforms, drilled from 2 platforms, and all these lines of receivers are secondary because they were just to check. We did several surveys. Here is the picture how we produced like all these sections between each receiver in each well. It's an offset VSP geometry. So you have one source and receiver, and that gives you the 2D section. And you have 45 2D sections, not a 3D image, 45 2D sections, and then you have to interpret them. So a vintage is produced every 2 days. Each source works for 2.5 hours. I don't remember, 2 or 2.5 hours. Then it switches different source, different source. We didn't experiment with running sources simultaneously. That's also a possibility, but we didn't do that. Separating them, it's going to be tricky. So, and they only run in daytime, not to disturb any people, you know, just to be sure. I mean, and comply with the noise regulations in Victoria, but actually they won't disturb anyone, but just in case. So we do it so that it takes 2 days to run 9 sources, and 2 days produce a vintage. Now the amount of data is enormous, so you see it's 200 terabytes a day. No, each vintage, 200 terabytes for 2 days, and then processing is done automatically that we implemented on computer infrastructure that we purchased and installed in the Otway site. So we've done completely autonomously. This proxy sort of software that we done, it's very relatively simple. So initially was done in a commercial package and then implemented in MATLAB standalone package that produces these kind of migrated images every 2 days and send it by internet. Now we get also pre-processed data, I think probably to this kind of level, also sent by internet. But not the raw data. The raw data is sent by tapes by normal mail. So there is a farmer that comes every few days and changes the tapes and sends the tapes by Australia Post. So in Perth, we have all the tapes, but we never open them again. So all automated, which was extremely important during all sorts of border restrictions in Australia during the pandemic, because we ran this project during the pandemic. And there's no people on site except the locals. These are kind of results. So these illuminated lines are where we detected reflected signal, more signal, and here is I told you there was a project where we did the 4D seismic, and then we did this new project. So there are 2 different plumes of CO2, and we see signal somewhere close to this second plume, the old one, which is interesting how this new CO2 merged with the old CO2. It was up deep, it was injected down deep from the old plume. So there's some anomalies here. So this is after injection of 15,000 tons. So the two plumes apparently merged. So this is all reflection seismic. So these are reflection anomalies that of reflection seismic changes of reflection amplitudes along these transects, 2D transects. So again, this is interpreting these kind of sections that's drawn here. Okay, I somewhere have a movie how this anomaly is created. You know, it's at different sections, as simple as that. The different sections between before injection and after. So this is a reduction of data from 200 terabytes a day, 200 terabytes a day to an amount that could be sent by internet.
How much do you have on tape?
Petabytes. But we never go back to the tapes. We have them archived and send us to Perth to be archived, but we never ever touch them. It's all automatically processed, pre-processed, because you know this processing that is done on site is kind of a little dumb. It processes every vintage independently, as if other vintages didn't exist. But then you do better job with time series analysis, if you like. So, and that way, we had a PhD student dedicated to improving specifically various processing things. And one of the things he noticed, which I didn't want to talk about too much, but just mention this in passing, is that because of the seasonal variations of the near surface, each day you can find a baseline which is better suited for that particular day. Better suited because it was kind of run at the same weather some time before the injection. Because we run 7 months of acquisition before the injection, we had 7 months of baseline to choose from. I'm not talking single vintages. We obviously combine vintages to increase signal to noise ratio, but that is part of this advanced processing sort of sequence that's done in-house, not on site. Yeah?
Maybe I missed it. What is the typical depth range for CO2? What is the depth range for CO2? The injection.
The depth range.
1,500 meters. 1.5 kilometers depth. 1.5 kilometers.
But the depth is from 8 hertz to up to 100 hertz. Is it sensible to this depth range of CO2?
What?
The depth data.
That data has very wide frequency range.
Yeah, from 8 to 100.
What do you mean 8?
I see the figure.
Maybe source.
Oh, yes.
Source from 8 to 120 hertz.
Oh, that's
Yeah,
okay.
the dust can work from millihertz to kilohertz. Well, not with this gauge length. So with this gauge length, maybe from millihertz to 100 hertz.
It's too high.
Yeah, we have experiments where we run dust in 15,000 hertz, 15 kilohertz. But it's, you can detect the signal, but you can't really look at the waves because our gauge length, effective length of the sensor is 10 meters. So it's much bigger than the wavelength and those frequencies. So we need much smaller gauge length to do that. But you can probably design a sonic log tube based on that, but you need a different kind of cable. Yeah. Anyway, so this is how these reflection amplitudes look. This is a classic sort of vertical seismic profiling kind of technology. Just 45 different transects going 5 wells with receivers and 9 sources. So what I wanted to talk about today mostly is actually passive acquisition without any sources. Okay, so this is reflection seismic was the mainstay of that project to detect CO2 plume, to map it. We injected CO2, we mapped the plume with reflection seismic, but we did 2 years of continuous data acquisition, all sorts of events. And that part of the presentation will be a little disjointed because we looked at various aspects of the signal that we see. Okay, and this is what I wanted to talk about. The first thing I was talk is completely sort of, it's not even, well, basically, if you have an earthquake, it is kind of almost theoretical. If you have an earthquake wave comes vertically from the bottom up, right? They are diving waves. They come, should have a picture. So I do have it somewhere, but earthquakes don't come, waves don't come horizontally. The body waves, at least, the body waves, they go down and come through the fast layers like the mantle or, you know, continental boundary, and they always come like this. Now, the strain in the rock in a particular place is bigger where the rock is softer. As simple as that. And here is a correlation between amplitude of the wave from an earthquake and this kind of quantity obtained from sonic logging. Well, sonic and density logging, sorry. Density logging. So rho is density, VP is P wave velocity, sound velocity. And this kind of, this is my rock physics contribution to this. So I derived this formula. And the correlation is pretty good. Now, it's not perfect because there's lots of assumptions in this. So particularly where you have big contrasts, it doesn't really work because it assumes that energy flux in the wave is kind of constant within the wavelength. Now, that's only true if you don't have a huge contrast. And of course, the range of investigation around the borehole with a sonic and earthquake wave of 1 hertz or something is different. But anyway, this proof of concept that this kind of thing can work. And we published a paper about using this as a kind of a proxy repeat log. And now I show you some data. So we run this well, injection well, below the reservoir, 100 meters below the reservoir. And here is a use of that technology, that idea, to see the amplitude of the wave. So you see, this is the moment the injection started and the amplitude has jumped, right? And remained almost constant here. The amplitude. And this is because, this is because the rock became softer. So yeah.
How do you adapt the original time error compared to the direct wave? What is the
This is all direct waves. This
is there any original time error?
No, I don't think we adjust for that. So what is happening is that the reservoir is 12 meters thick. So it doesn't really affect your velocity model hugely, you know? So for imaging the reservoir itself, there's no issues. We didn't adjust the velocity model for that because velocities above the reservoir are the same, they're not changing. So, but here on the plot, by the way, is modeling versus the data, and the modeling is done for notional thickness of 11 meters. We did modeling for all sorts of thicknesses, but this is thickness of 11 meters. Now, There's also travel time change, as you mentioned. So the travel time change is because, again, this rock becomes softer. As it becomes softer, it's actually slower.
What do you mean by something? Rock is something.
Well, you injected CO2, you displaced water, so it's softer.
You mean modular, isn't it?
What?
Modular, elastic modular.
Yeah. You're right. So the modulus, the compressibility is higher because CO2 displaced water. That's, my bread and butter, which come from rock physics originally. So yes, so you replaced basically water with the, roughly say, gas. It's not really gas, it's in supercritical state. So it's a supercritical fluid, but it's very compressible. Not as compressible as gas, but it's 2 orders of magnitude more compressible than water. So it's almost, so and maybe only 10% saturation. Only 10%, but it's enough. You put mixture of water and gas will control the compressibility, So, and basically the travel times, they're only, 0.5 milliseconds, but it's very reliably, clearly seen, right? So have a travel time change, half a millisecond. It's not a lot. For those people who are kind of familiar with the seismic, half a millisecond is not a lot, but our discretization usually is 2 milliseconds. So half a millisecond, not a lot, but very reliably, you can see. And basically, if you compare the prediction, which is red, and the model, which, and the data, which is black, you see the difference. And the difference is caused by the fact that the model was actually 1D. It's a simple layered model. It did 1.5D, it's called. So full 3D propagation in a 1D medium. But the model, the real plume has a finite lateral size. That's why it diffracts around it. So you see a decrease in the amplitude as it diffracts around, the little waves diffract around it. It's only maybe 100 meters. The border of the plume is probably 100 meters away from the injection well. Because if you look at the shape of this thing here, injector is here and the CO2 is moving this way. So it's not far the edge here. We also observed natural seismicity, and I can talk a lot. This is kind of earthquake. It's another earthquake, another earthquake. These are earthquakes. And we try to use, now, what I forgot to say, guys, sorry, my fault. Here it is a signal from this permanent source that we have. It's not from earthquake. Obviously, because I showed the travel time difference, it's from a source, from a permanent source, the closest to the well, SOV9. So this is from the source, permanent source, a very clear amplitude. So this you can use, for example, if you want to do what we call a 4D well tie, seismic to well tie, to tie seismic to the wells. But it would be useful, you can do that without any source, basically. And we try to do that, mixed results. So first of all, we located lots of these earthquakes. So these earthquakes, we located lots of these earthquakes here. So we had 5 wells in a small area, which was not enough to accurately locate them position. Azimuth, yes, azimuth we could. No, I'm lying. Distance we could. Azimuth, because it's so small aperture, we couldn't see that reliably. We kind of ballpark, yes, but not reliably. But that's not important. So we actually located microseismic, local seismicity, regional seismicity, and global seismicity. Everything we located. we saw, but we focused at the moment on the regional earthquakes, and we kind of looked at all of these seismograms, and you can see the seismograms that from the earthquake which occurred after the injection. They all have this little peak of amplitude and dim line here. So on this screen here, I can't see, but you should see that somewhere where these arrows are. There's like going through all the waves, a kind of disturbance. And that's because this layer suddenly injected with CO2 is softer than it used to be. And it's softer than surrounding rocks, actually, because these are not time-lapse differences or anything. These are natural seismograms. So you see these peaks. It's far less pronounced than with the active source. You know, much less crisp. Only because the effect was large that we could see it. So these peaks here, they're troughs actually. So this is not the best picture. This dim dotted line is kind of log data, this kind of property. And the blue lines are the field data. But nevertheless, the trough here is very pronounced. And before injection, it isn't. Yeah.
Can you go back one slide? What do you make of the fact that it looks like the amplitude of the peak that you're pointing out varies through time?
It's every earthquake is different. It has different frequency content. That's the main thing. Different frequency content. They also we kind of see that the reliability of this method varies. We use it also in Western Australia. We have a lot of data from Western Australia, and it didn't work as well as in Otway, for example, for us in terms of correlation with the known properties. And the reason we identified as having interference of so-called ghost waves. So the wave that comes through from the bottom, earthquake wave comes, and then it reflects from the surface. As they interfere, they actually kill some frequencies. And this is something, if you had extremely broadband, we also kind of interesting. We experimented with the teleseismic events, which come from much larger distances, and we couldn't get anything from them. Which this effect should be from any earthquake, but you couldn't get. And you need really broad band. You know that those earthquakes further away, they're depleted with high frequencies, and you need a very broad band, and we haven't solved this problem yet. This interference is actually very detrimental to what we do. But we haven't figured out how to, because it's work in progress, basically. I think we will find, maybe we use some neural net or something, you know, to kind of, but once you kill these frequencies, you can't just, even like there are methods actually for this, because we published this a few years ago, this paper, and there's some other people took up this kind of technology and say, well, we can do better with separation up and down going waves, which is obviously easy because you have receivers at every point. So they did that, but it doesn't really solve this problem, because once you lost those frequencies, you can't get them back. That's what people who understand signal processing better can explain to me. Once you lost them, these frequencies. You can't get them back. So no magic thing. They are not in your receiver, you know? And so it's kind of interesting. This is the biggest earthquake in Australia in recent history, the recent 100 years. So also has this kind of anomaly. This was happening. This earthquake happened when I was here in the US in September 2021 under special permission from the Australian government, which had closed the borders even for people living in the country. And a relative of mine sent a WhatsApp message. I think we had an earthquake. he was in the shower at that moment. I immediately called out, sent a message to my colleague in Perth and saying, there was a big earthquake. Well, 5.7, take it as big for Australian standards. And basically he said, well, has nothing in the media yet, but our receivers, I think they show something because we have this continuous recording, where we can check it from Perth every minute. And it was, then yes, of course, this was the biggest earthquake. Induced seismicity. So I really don't want to talk too much about induced seismicity, that we see induced events. So we inject CO2, it produces some earthquakes, small, micro earthquakes. Don't want to scare anyone. Now, people who are familiar with this CO2 technology or where it's all going, CO2 injection technology, know that the seismic risk is one of the biggest obstacles or risks, let's say, that people consider when they consider geological carbon storage, because they're afraid of fault reactivations, CO2 leaking through the faults, but also the seismic risk itself. Maybe we will produce earthquakes that are damaging or something. Now, these earthquakes are not damaging, they're extremely small, they're magnitude 0 or smaller, but they do exist, they reliably can be detected. And what is interesting about these earthquakes is they all occurred in the same fault. And they appear to occur where the CO2 saturation front reaches that fault, not the pressure front, as you would expect. Fluid, when you inject fluid into a well, into a reservoir, the first thing that happens is that you injected some pressure, the pressure starts propagating. The actual CO2 front is much slower. I think order of magnitude slower. Those familiar with the biotheory know that fluid pressure is basically a bioslow wave. Well, that's maybe I'm expecting too much, but it's so now people have speculated why this is so. Why CO2? What does it change? What CO2 changes? Stanislav Glubakovsky, who used to work with me in Perth and is now at Lawrence Berkeley National Laboratory in the US, he's keen to come here to give a talk about specifically induced seismicity in this project, because he led the analysis of this local seismicity data, both for the previous injection, where we detected it using 900 geophones on the surface, and this injection, which has much more sensitive instruments, the distributed acoustic sensor in every well, especially much closer to the actual sources, but we did not see many more events. We saw a similar number of events. We have been speculating why we can't see smaller events, really smaller, maybe magnitude -2, maybe -3. And we concluded that the reason we don't see, and we want to see the Gutenberg-Richter law, which is that for each large event, you will have to see more smaller events and even more smaller events and so on, until you run to the threshold of your equipment. But we don't see that. And the reason we don't see that, we speculate, is that because of limitations on our sensors, because our sensors have this gauge length of 10 meters. They can't really see high frequency. Small events are high frequency events. We can't see high frequency waves with a 10-meter gauge length because it's so much bigger than the wavelength, So even though the sensors themselves can sense a signal of 15 kilohertz, and we had a source in the well that produces this kind of a piezoelectric actuator that we put in the well that produced this, we saw that. But it's detecting signal right next to it, it's one thing. But the waves, it won't detect because of the averaging in the gauge length. So we speculate that these events, which has hundreds of hertz, not kilohertz, but hundreds of hertz, we can't see. So work in progress. Now with the current cables, which are perfectly valid, they still work and stuff. We cannot do anything with by decreasing weight gauge length, but and the injection's finished anyway, so there will be new injections there. There will be a new project with injecting similar amount of CO2 in a kind of pulsed injection, and I don't know why they want pulsed injection. Maybe that's just improving the sweep efficiency as a separate project, together with Japan, funders from Japan and Korea, and there will be opportunities, but I don't know if there's any plans to do a different kind of gauge length to see more induced seismicity. And there's also on the horizon plans to inject hydrogen, but I think that might be in a depleted gas reservoir rather than in the aquifer, for reasons which I don't think we have time to talk about. But there's a pressure response. Now, it's a different thing. I mentioned that DAS, the distributed acoustic sensor, the fiber optic, has an amazingly broadband receivers. And here is an example of the DAS data, depth in the vertical axis, time in hours on the horizontal axis. And this is injection of CO2, a pulsed injection kind of. And blue is the pressure in the injection well in PSI. And this is in the monitoring well. So this is in the monitoring well, it's called CRC5. And I'll show you a better picture. Here on the left, you have a zoom in on that picture. And blue is pressure derivative of pressure, time derivative of pressure. Okay, how do we say? Rate of pressure, of change of pressure. And the black is the DAS response at that point in the reservoir. DAS is from 0 meters installed to the 1600 meters, from 0 to 1600. But this is zoom around the reservoir, 1700. And there's a Bayesian correlation between the pressure signal, and the amplitude of the DAS signal. So the periods here is hours. So that's how low frequency we can see. Now you have pressure change over a month, you won't see it because it measures derivative will be too small. You need to use a distributed strain sensing, which is easy. We just purchasing a system that would do that.
That just means changing the interrogator?
Yeah, it's a different interrogator. It's a different interrogator that uses a different type of scattering. So it's not a Rayleigh scattering, it's some other scattering. I don't remember which one. I think a Brilliant scattering. So there are even combined systems, but I think our guys want to buy a strain system separately to be more volatile. And you know, each of these cables has several fibers, optical fibers. So you can connect one to DAS, the other to, and there might be engineered cable for DAS. Brilliant scattering is different, it's molecular, whatever it is, it's just different thing, and then you can get the strain sense. But strain sensing is not as sensitive as the seismic sensing, so you wouldn't get this necessarily nano strains, you know. So that's what I'm told, you know, because these are, you see, the sensitivity here. This is nano strain per second. It's very, very small. The other thing we see is ocean microseisms. So basically, this is basic signal. And all of these little red things are kind of small storms. So this is spectrogram, so this is frequency, and this is time. And you can get this picture for like 1 second. I'll just show here for every depth as well. So this is depth, frequency, and time. So we do this kind of analysis and then we do the sections. So these red things are signatures of kind of storms. What happens is that waves in the ocean, I mean, for these kind of frequencies, there's no other seismic source that could produce frequencies of this. You need just too big a source, you know? So on land, there's no such sources, except maybe earthquakes. But earthquakes don't occur every minute. So in the absence of earthquakes, you have this ocean that produces energy. Now, I'm told by people who understand nonlinear waves that actually this is as waves propagate in the ocean, they actually non-linearly interact to produce waves in the bottom, in the ocean bottom, and then propagate on to the land. Now, this site is 4 kilometers from the beautiful coral coast of Eastern Australia, but even in the middle of Australia or in Moscow somewhere, at these frequencies, the ocean is still the dominant source of seismic energy. Everywhere. But maybe they will diminish. But yeah.
I wonder if this will vary depend with their depth, their dominant frequency range.
Yes, of course, because these are Rayleigh waves. There's a lot of evidence that what we see primarily are Rayleigh waves. Sometimes love waves, but mostly Rayleigh waves. And Rayleigh waves will diminish with depth, but depending on the frequency, I'll show you the pictures. I have slices in this. Well, this is depth slice. So a kind of diminishing frequency here, you see? And it's also interesting that if you look more carefully, which is not really, this picture is not very good, the amplitude also varies vertically, even at the frequencies where you still have energy. And that is actually a powerful tool that we are developing now to actually use these to do logging, to understand correlation, to map the properties of the medium using amplitudes of the ocean waves, or these Rayleigh waves. You see more than that. At the very top, you see this is probably traffic and stuff, and there's a different depth. So what you asked, this is against depth here, and this is a different depth. So very strong at the 20 meters depth, 100 meters. But you see them even at 900 meters depth. This is cheating because this is not at Otway. This is actually in our well on the campus. We have 900-meter well. If you want to do some experiment there, you can. We have a dedicated to our group, 900-meter well. Fiberglass, cased with fiberglass, and a fiber optic cable behind the case. So 900 meters is the maximum we can go to. No injection of CO2. No injection of any kind except water. Water, we have injected water. So we are allowed to inject water. But nothing more than that. And this is all traffic. This is all traffic. So the higher frequencies between 10 and 100 hertz, it's all traffic. And traffic, you see, changes every day. These are days of traffic, you know. At night, there's less traffic. And you see, even at 900 meters, you still have traffic, which is kind of funny. High frequencies, they might diminish amplitude, but they not kill the amplitude, you know? Amplitude is not killed, which I'm surprised. It's much stronger here, but you still have traffic. And below below 0.1 hertz, I think this is instrumental noise. You can occasionally see some strong storm coming here, but mostly this is some sort of. I'm told that this is some temperature effects within the system. Temperature. This thing is sensitive to temperature. You can correct for it, but I don't think we can interpret data here. And you see, this is a big storm, and a gap in the middle, because people switched off the equipment to save it. Because a big storm, you know, so. This is specifically looking at traffic. So traffic goes up and down. This is weekend. This is another weekend. This is a long weekend. So that's amplitude in a 4 to 22 hertz. This is a high frequency. Very good correlation, kind of with temperature, but obviously not the weekends. And then there is a storm here where temperature fails to change, but the traffic still strong. This is a much lower frequency, and this shows good correlation with the wind speed, not because wind causes any waves by itself, but because, well, there's something going on. Waves, local waves, not the waves that I talk about in the open ocean, but actually close to the shore, breaking waves, that kind of thing, when you have windy weather, causes, and you see correlation is non-existent when the wind is moderate, and normally when it's strong, this is, breaking waves at the shore. And this is in Perth, so it's not 4 kilometers from the ocean. This is about 20, would be probably 15 kilometers from the ocean, 20 in where our campus is, 20 kilometers from the ocean.
Why do you say,
Different ocean, it's an Indian Ocean. I don't think it matters.
why do you say it's ocean waves, not trees blowing in the wind or buildings? Is it the frequency?
I can't guarantee that. No, the frequency is too low. You need a big source, like wavelengths, kind of, so this is 0.6 hertz, so you need big source. But I mean, I don't know categorically, This is a nice picture of the earthquake. You see, when earthquake does occur, it kills, you can't see any ocean noise anymore. So strong it is. So this is a remote earthquake. This is from Sumatra, probably. And these are P waves. The word P waves we use for longitudinal waves. But actually, the terminology comes from the ocean, the earthquake seismology. And the seismologists call this P waves because the primary wave, the first one, arrival. Then S wave, this is a secondary wave, which we call shear wave or transverse wave. And this is a Rayleigh wave. It has this dispersive character, the low frequencies and higher and higher and higher. So these are Rayleigh waves. And the Rayleigh waves have most energy. And you see, it's a very broad band, so we tend to think that remote earthquakes will be just low frequency, but actually most energy is at low frequency. This is like 0.10, 100 millihertz, maybe less, but it goes up several hertz, particularly body waves. Not so much the Rayleigh waves, but the body waves. And we now have this picture for every depth as well. Not that they change that much. And this is traffic. Basically, that's it. Thank you.
let's take a few minutes for a few questions if anybody has anything I maybe interrupted enough already.
Yeah, so I have a quick question. So you showed some plot